In this video, I'll be walking through the answers to my Level 2 electricity workbook. A link to the PDF and a list of corrections is in the video description. Charge. Question 1. Draw arrows on the diagram below to show the forces experienced by each charge. We have two positive charges, a positive and a negative, and two negatives. We know that like charges repel, so that two positive charges will experience opposing forces, as will two negative charges, and we also know that unlike charges attract. So if we have a positive and a negative, their forces are going to be towards each other, or in other words, attractive. Question 2. Calculate the amount of electrons required to make up 1 coulomb of charge. And so we know that our charge is 1 coulomb, and we know the charge of the electron is 1.6 times 10 to the minus 19 coulombs. Putting this all together, we know that our charge, which is our 1 coulomb, is equal to some number n multiplied by the charge of the electron. Rearranging that for n by dividing both sides by the charge of the electron E, substituting in 1 coulomb and also 1.6 times 10 to the minus 19 coulombs. Our coulombs here cancel, and we just get 1 divided by 1.6 times 10 to the minus 19, which gives us 6.25 times 10 to the 18, or 6.3 times 10 to the 18 to 2 significant figures. Question 3. As a passenger exits a vehicle, friction between their clothing and the car's interior fabric can cause them to become positively charged. Explain how this buildup of charge occurs, and what effect this has on the interior fabric. As our passenger is exiting the vehicle, friction removes electrons from the passenger's clothing and deposits them on the car's interior fabric. Because the passenger's clothing has lost negatively charged electrons, it now has more positively charged protons than electrons, making it positively charged. As the passenger exits the car, they receive a shock from the metal exterior. Explain what causes this to happen. We know that the passenger is positively charged because we're told so in the setup to this question. We also know that cars have a metal exterior and that metals have electrons that are free to move. They are electrically conductive. When the passenger contacts the metal exterior, these electrons are attracted onto the positively charged passenger, since unlike charges attract, which causes the passenger to receive a shock. So it's these large amount of electrons flowing into our passenger's hand, which causes the electric shock. Discuss how holding on to a metal part of the car while exiting might prevent or reduce this shock. As the passenger loses electrons when they rub against the car's interior, the lost electrons will be replaced by electrons flowing from the metal part of the car. This will reduce the buildup of charge on the passenger and will therefore reduce the severity of any shock they might receive. And so even though the passenger is still losing electrons and they're still receiving electrons from the metal part of the car, something that previously resulted in an electric shock, because we are replacing these electrons gradually rather than in just one big jump, any shock that the passenger is now going to experience will be much less severe. If the passenger gains a charge of 3.2 times 10 to the minus 6 coulombs, calculate the number of elementary charges, aka electrons, that they have lost. So our charge is going to be some number times the charge of the electron, rearranging that for n by dividing both sides by E, putting in our total charge, and dividing that by the charge of the electron. We're essentially finding how many times this charge of the electron fits into our total charge. That amount is 2.0 times 10 to the 13. Question 4. A physics teacher rubs a plastic rod with a cloth, causing the rod to become negatively charged. Explain the effect this has on the cloth. Because the rod has become negatively charged, the plastic rod must have gained electrons from the cloth. Because the cloth now has less negative electrons than positive protons, it will have become positively charged. And it's this statement here that is crucial to explaining why we now have positive charge. It's not enough to say that they just have become positively charged, and it's incorrect to say that they've gained positive charges because we know that the things moving are negative electrons. We must link it back to the positive protons and the fact that there are now more of those than our negative electrons. Discuss what would happen if the negatively charged rod were brought close to a negatively charged balloon. The negative electrons in the rod and the balloon would repel each other, causing the balloon and rod to experience a force away from each other. since we know that like charges repel. If the rod gains 2.0 times 10 to the 13 electrons, calculate the total charge on the rod. Once again, we know our total charge is some number times the charge of the electron. We know that there are 2 times 10 to the 13 of them, and we know the charge of the electron, which gives us 3.2 times 10 to the minus 6 coulombs. Question 5. A student places their hand on a Van de Graaff generator. They feel their hair stand on end as they build up charge. Explain what causes this to occur. When the student places their hand on the generator, they become charged. Because their hair has also become charged, and they all have the same charge, each strand of hair is repelled from every other strand of hair. This causes the hair to stand on end. And so as the hair stands up, it's doing so because every strand of hair is negatively charged, and therefore every strand of hair is trying to get away from every other strand of hair. There is a repulsive force between them. Electric field lines. Question 1. What direction do electric field lines point? Electric field lines point in the direction that positive charges experience a force. They therefore point away from positive charges and towards negative charges. Since a positive charge will experience a force away from a positive charge, and a positive charge will experience a force towards a negative charge. Question 2. Add arrows to the diagrams below to show the direction of the electric field lines. We first have our positive charge, and we know that field lines point away from positive charges. For our negative charge, we know they point towards a negative charge. And for our negative and positive plate, we know that the lines must point away from the positive and towards the negative. Question 3. Label the diagrams below with the correct charges. For our first diagram, we have 2 charges. The field lines are pointing away from one, which means it must be the positive charge, and towards the other, which means it must be a negative charge. For our second diagram, we have a charge above a plate. The field lines are pointing away from the plate, which means that must be positively charged, and towards the charge, which means the charge must be negative. For our last diagram, we have 2 charged plates. The field lines point away from one, which must be our positive, and towards the other, which must be our negative. Question 4. Explain how electric field lines are used to show the relative electric field strength at any location. The relative strength of an electric field at any location is indicated by the closeness of the electric field lines. The closer the electric field lines are, the stronger the field. So if we look at this diagram, for example, we see that in this region here, our field lines are relatively close together, and so there must be a relatively large electric field. Whereas for this region here, the field lines are relatively far apart, and so we must have a relatively weak field. Question 5. Draw the electric field lines between the charges in the diagrams below. In our first diagram, we have 2 positive charges. Because our positive charges repel, our field lines are going to appear to repel as well, and furthermore the direction of the field lines, because these are positive charges, are going to be away from the positive charge. For our second diagram, we now have unlike charges. We know that unlike charges attract, and so their field lines appear to do so as well. As for the direction, we know that the field lines are going to point away from the positive and towards the negative. These field line diagrams might initially seem like they'd be hard to remember how to do, but on the upside, there aren't many variations that we'd ask you to do. In fact, for this particular standard, Level 2 electricity, this page covers them all. And after a little bit of practice, you might be surprised at how quickly they become second nature. Question 6. Use the diagrams in the previous question to justify which situation produces the greatest electric field strength between the charges. Going back to our previous page, we know that electric field strength is indicated by how close the electric field lines are. Between these 2 diagrams, we see that the field lines are closer in between our unlike charges than at anywhere else. The closeness of the electric field lines indicates the strength of the electric field. The lines are closer together between the 2 unlike charges, so the electric field strength is stronger compared with the like charges. Question 7. Draw electric field lines between the parallel plates in the diagram below. We have our negative plate, and we have our positive plate. Our electric field lines between 2 parallel plates are going to be parallel, and they're going to point away from the positive and towards the negative. Also important is that they are equally spaced. At the edges, however, we see a slight curving to the field lines because we have some charge on these exterior surfaces. When drawing this in an exam, there are 4 things the examiner will look for: that the field lines are parallel, that they are pointing in the right direction, that they are equally distant, and that the field lines are curved at the edges. Question 8. By observing the path of the charged particles below, label each charge as positive or negative. So we have a negative and positive plate, and we have some charge which is deviating towards the negative plate. Because it's being attracted to the negative, it must be positive. On our second diagram, we have our positive and negative plate. We have our charge, which is deviating towards the positive plate. Because it's being attracted to the positive, that means it must be negative. Question 9. Draw the path of each charged particle as it moves between the parallel plates below. We have our negative and positive plate and a negative charge. The negative charge is going to be attracted to the positive plate, and so we're going to see it deviate in that direction. On our second diagram, we once again have our charged plates. We now have a positive charge, which because it's positive means it must attract to the negative, so we see it deviate in that direction. Question 10. Describe 2 ways to increase the electric field strength between 2 parallel plates connected to a voltage source. We know that electric field strength is described by the equation E equals V over D, which is voltage over separation. Therefore, either increasing the voltage or decreasing the plate separation will increase the electric field strength. Being able to use arrows to reason with an equation like this is a crucial skill that, if you haven't already, you must be sure to develop. Question 11. Calculate the electric field strength between the following parallel plates. 2 parallel plates, 5.3 centimeters apart, are connected to a 9-volt battery. So we know our separation is 5.3 centimeters, which is 0.053 meters. We know that E is equal to V over D. Our voltage is 9. We know our separation, which gives me 169.8 or 170 volts per meter to 2 significant figures. A 12-volt power supply is used to charge 2 parallel plates, positioned 0.04 meters apart. Once again, we know that E is equal to V over D, our voltage is 12, our separation is 0.04, which gives us 300 volts per meter. Question 12. Calculate the plate separation in the following situations. A 3.5 volt per meter electric field is created between 2 parallel plates connected to a 1.5 volt battery. To find our plate separation, we start with our E equals V over D equation, solve that for D by swapping the E and the D around, putting in our voltage and our field strength, gives me 0.4286 or 0.43 meters to 2 significant figures. 2 parallel plates are connected to a 300 kilovolt power supply, creating a 3.2 times 10 to the 6 volts per meter electric field between them. We know that our voltage of 300 kilovolts is 3 times 10 to the 5 volts. That is 300 times 1000, and we move our decimal point 1, 2, 3, 4, 5. We know that E is equal to V over D, solving that for D, by swapping the E and the D around, putting in our field strength and our voltage, gives me 10.67 or 11 meters to 2 significant figures. Electrostatic force. Question 1. A charge is placed in a uniform electric field. Explain how the direction of the force depends on whether the charge is positive or negative. A positive charge will experience a force in the direction of the electric field, whereas a negative charge will experience a force against the direction of the electric field. Question 2. Draw arrows on the diagrams below to show the direction each charge would experience a force. We have a positive charge in our first diagram, and as we know, positive charges will experience a force in the direction of the electric field. So we draw our arrow in the direction of the field. In our second diagram, we now have a negative charge. Negative charges experience forces against the direction of the electric field. So our arrow should point in the opposite direction. Question 3. Protons have an equal and opposite charge to electrons and have a much larger mass. If both enter an electric field with the same velocity, explain any differences in their travel paths. The electron and proton have an equal and opposite charge. They will therefore experience the same magnitude force from the electric field, but in opposite directions, as we saw happening in the last question. Furthermore, because the proton has a larger mass, it will have a smaller acceleration from the electric field, causing it to deflect less. We can think of this in terms of F equals ma. For the same amount of force, because our proton has a larger mass, it's going to experience less acceleration, and therefore it will deflect less. Question 4. Calculate the electrostatic force experienced by the following charged objects. A dust particle with a charge of -6 times 10 to the minus 15 coulombs enters a 8 times 10 to the minus 3 volts per meter electric field. To find the force, we use our equation from up here. Putting our electric field and our charge in gives us -1.28 times 10 to the minus 17, or -1.3 times 10 to the minus 17 newtons to two significant figures. A raindrop with -4 times 10 to the minus 14 coulombs of charge falls through a thundercloud's 1.5 times 10 to the minus 4 volts per meter electric field. Once again, using our force equation, putting our electric field and our charge in gives us -6 times 10 to the minus 18 newtons to two significant figures. Question 5. Calculate the charge of the following objects. A plastic bead in a 6 times 10 to the 3 volts per meter electric field experiences a force of 1.2 times 10 to the minus 8 newtons. Knowing our force equation, we can solve this for charge by dividing both sides by the electric field. Putting in our force and our electric field gives us 2 times 10 to the minus 12 coulombs. A pollen grain experiences a force of 7 times 10 to the minus 12 newtons due to a 1.4 times 10 to the 3 volts per meter electric field. Starting again with our force equation, once again solving it for charge, putting in our force and our electric field, gives us 5 times 10 to the minus 15 coulombs. Question 6. An inkjet printer aims droplets of ink onto paper by passing them through a uniform electric field. Each droplet has a mass of 2 times 10 to the minus 12 kilograms and is given a charge of 80 nanocoulombs. Calculate the electrostatic force on an ink droplet if the electric field is set to 2.5 times 10 to the 4 volts per meter. First of all, we know our charge is 80 nanocoulombs, which, because nano is times 10 to the minus 9, equals 8 times 10 to the minus 8 coulombs. We have our force equation. Putting in our electric field and our charge gives us 0.002 newtons. Calculate the acceleration of the ink droplet. To find the acceleration, knowing the force and the mass, we can use F equals ma, rearrange for acceleration by dividing both sides by the mass. Putting our force and our mass in gives me 1 times 10 to the 9 meters per second. Discuss what changes could be made to increase the deflection of the ink droplet. The deflection of the droplet is proportional to its acceleration. The acceleration of the droplet can be increased by decreasing its mass or increasing the size of the electrostatic force. We know this because F is equal to ma, and so to increase our acceleration, we would either need to keep the force the same and decrease the mass, or if we're keeping the mass the same, we'd need to increase the force. The electrostatic force can be increased by either increasing the electric field strength or by increasing the charge on the droplet. Since we know that F is equal to EQ, and so to increase the force, we can either increase the field strength or the charge on the droplet. Question 7. A 4 times 10 to the minus 6 kilogram water droplet is given a charge of -2.5 microcoulombs. Calculate the electric field strength needed to keep the droplet suspended between two horizontal parallel plates. Our charge is -2.5 microcoulombs, where micro is times 10 to the minus 6. For our water droplet to be suspended, our upwards force of the electric field and our downwards force of gravity must be equal to each other. We know that the electric force is EQ and that gravity is mg. We can solve this for our electric field strength by dividing both sides by q. And now putting in our mass, the acceleration due to gravity, and our q, we get 15.68 or 16 volts per meter to two significant figures. Question 8. A tiny oil droplet of mass 2.5 times 10 to the minus 12 kilograms is suspended between two horizontal plates. The plates are 5 millimeters apart, and a potential difference of 480 volts is applied across them. The droplet remains stationary when the electric field is present. Draw a force diagram showing all the forces acting on the oil droplet. And so we have our two parallel plates, and we have our oil droplet. We know we're going to have a downward force due to gravity, and in the opposite direction, to keep our droplet suspended, we must have our electric force, which is equal in size. So we need to make sure that the length of these two vectors is the same. Calculate the gravitational force acting on the oil droplet. We know we can find the force of gravity using F equals mg, where we know the mass, and we know the acceleration due to gravity, which gives us 2.45 times 10 to the minus 11, or 2.5 times 10 to the minus 11 newtons to two significant figures. Calculate the charge on the oil droplet. To find the charge, we can use the force equation, that F is equal to EQ, solving that for charge by dividing both sides by the electric field strength. And while we know the force, we found it earlier, we don't know the electric field strength, so we need to find that. To do so, we can use the fact that E equals V over D, where we know our voltage, we were given it in the question, and we know our distance was 5 millimeters, which is 0.005 meters, which gives me 96,000 volts per meter. Putting that into our charge equation gives us 2.552 times 10 to the minus 16, or 2.6 times 10 to the minus 16 coulombs to two significant figures. Explain how the forces on the droplet would vary if it were moved towards the positive plate. The gravitational force depends on the mass of the droplet, since we know that this force is mg. The electrostatic force depends on the charge and the electric field strength, since we know that F is equal to EQ. The electric field strength depends on the plate separation and the voltage, since we know that E is equal to V over D. Moving the charge does not affect its mass and charge, and neither does it affect the plate separation or voltage. Therefore, neither the gravitational force or the electrostatic force will change if the charge is moved. Electric potential energy. Question 1. State whether the charges in the diagrams below have lost or gained electric potential energy. In our first diagram, we have a positive charge moving with an electric field. Positive charges experience a force in the direction of the electric field, and so to store energy in the electric field, we would need to move against this force. Because we're instead moving with the force, we have lost electric potential energy. In our next diagram, we have a negative charge moving at right angles to the electric field. Because the electron is neither moving with or against the field, there is no change in its electric potential energy. In our next diagram, we have our negative charge moving with the electric field. Negative charges experience forces in the opposite direction to the electric field, and so because we're moving against the electric field, we are storing electric potential energy. Therefore, we have gained electric potential energy. In our diagram here, we once again have a negative charge, in this case moving against an electric field, but it's taking a little bit of a curvy path. Regardless of its path, it's moving against the electric field, and because it experiences a force against the field, a force that it's moving in the direction of, it is therefore not acting against this force, and it's therefore not storing electric potential energy, it is losing electric potential energy. In our next diagram, we have a positive charge, and it's moving against an electric field. Once again, positive charges experience forces in the directions of the field. Because we are moving against this force, we are storing electric potential energy, and we have therefore gained electric potential energy. In our last diagram, we have a negative charge, and it's moving against the electric field, and then it's moving with the electric field, such that it returns to the same level. And as mentioned before, our negative charges experience forces against the direction of the field, And so what has occurred is our negative charge has stored energy as it's worked against the field, and then as it's changed direction, it has started to lose that electric potential energy again. Because it's returned to the same level, all of the electric potential energy it's gained, it has now lost, and therefore we have no change. Question 2. The diagrams below show protons being moved in a 48 volts per meter electric field. Calculate their change in electric potential energy. We have a positive charge moving against an electric field. Electric potential energy is EQD, where we have the electric field strength. We were given it up here. We have the charge of our proton, which is the same as the charge of the electron, except that it's positive, and we have the distance that it has moved in the electric field. This gives us 1.843 times 10 to the minus 19, or 1.8 times 10 to the minus 19 joules to two significant figures. In our next diagram, we have our proton moving a distance of 1.2 meters, but this time at an angle of 40 degrees to the field. Once again, our change in our electric potential energy is EQD. We have our electric field, we have our charge, but for our distance, we need to use the component of this triangle here. This is the opposite side of our right-angled triangle, where 1.2 is our hypotenuse. Remembering SOHCAHTOA, the SOH relationship says that sine of our angle, which is 40 degrees, is equal to our opposite, which is what we're trying to find, divided by our hypotenuse, which is 1.2. To solve for our question mark, the component that we're trying to find here, we just multiply both sides by 1.2, which gives us 1.2 times sine 40, giving us 5.924 times 10 to the minus 18, or 5.9 times 10 to the minus 18 joules to two significant figures. In our last example, we have a proton traveling 11 centimeters. However, this distance is at a right angle to the field, and so the distance against the field is 0, and so our change in our electric potential energy is also going to be 0. Question 3. A small one-man starfighter fires a proton torpedo towards a small thermal exhaust port. The exhaust port is protected by a ray shield, which creates a 25 centimeter thick electric field. The mass of a proton is 1.7 times 10 to the minus 27 kilograms. Calculate the kinetic energy of a proton traveling at 3 times 10 to the 7 meters per second. We know that kinetic energy is half mv squared, where we know our mass and we know our velocity, which gives us 7.65 times 10 to the minus 13, or 7.7 times 10 to the minus 13 joules to two significant figures. Determine the work the electric field must do to stop a proton traveling at this speed. In order to stop this proton, we need to reduce the kinetic energy to 0, and so the work that we need to do to accomplish this is exactly the kinetic energy that we just found. Calculate the electric field strength the shield must produce to bring the proton to a stop. So we know that our electric field was 25 centimeters thick, or 0.25 meters. We know that the electric potential energy is EQD, and we're choosing this equation because we know the change in potential energy required. That was our kinetic energy that we found in A. We want to find our electric field strength, and we know our charge and we know our distance. So to solve this for our electric field strength, we just divide both sides by QD, put all of our numbers in, which gives us 1.913 times 10 to the 7, or 1.9 times 10 to the 7 volts per meter. Question 4. Two parallel plates are connected to a 12-volt battery and positioned 5 centimeters apart. A 4 times 10 to the minus 6 kilogram particle carrying a charge of negative 2.5 microcoulombs moves from one plate to the other. Calculate the electric field strength between the plates. Our distance of 5 centimeters is just 0.05 meters, and to find our electric field strength, that is just voltage divided by distance, where we know the voltage and we know the distance, which gives us 240 volts per meter. Calculate the force acting on the particle due to the electric field. We know that force is equal to EQ, where we just found our electric field strength E, and our charge is 2.5 microcoulombs, where micro is times 10 to the minus 6. Putting these numbers in gives me 6 times 10 to the minus 4 newtons. Calculate the change in electric potential energy of the particle. Our electric potential energy is EQD, where we know all of these things, which gives us 7.2 times 10 to the minus 3 joules. Calculate the final velocity of the particle. To find our final velocity, we can use the kinetic energy equation. To solve this for velocity, we first double both sides and swap them around. We then divide both sides by the mass, square root both sides, and then put our numbers in to find 60 meters per second. Discuss how the final velocity of the particle would change if the plates were closer together. Decreasing the plate separation increases electric field strength, as E is equal to V over D. And so with our E is equal to V over D, keeping our voltage the same, while decreasing our plate separation is going to increase our electric field strength. The final velocity depends on the kinetic energy gained, which is equal to the electric potential energy lost, which as an equation is delta E equals EQD. And now since the plate separation decreases and the electric field strength increases in equal proportion, their effects on the electric potential energy cancel. The final velocity of the particle is therefore unchanged. And so we know that our change in energy is our EQD. And if we keep our charge the same, decreasing our distance, as we know, also increases our electric field strength in equal proportion. These effects are going to cancel out, leaving our electric potential energy unchanged. If we were to put this in more of an intuitive way, although we have increased our electric field strength, which seems like we should increase our energy, because we've also decreased our distance, the particle is moving a smaller distance through this field, such that the effects cancel out. Question 5. A thundercloud forms above a city, producing a uniform electric field of 2.5 times 10 to the 4 volts per meter beneath it. The potential difference between the thundercloud and the ground is 3 times 10 to the 8 volts. Calculate the height of the thundercloud above the ground. We know that our electric field strength is volts over distance, where we know our voltage and we know our electric field strength, so we just need to solve this for the distance. To do that, we can swap our E and our D around, put in our numbers, which gives me 1.2 times 10 to the 4 meters. A 3 times 10 to the minus 5 kilogram raindrop with 2.1 times 10 to the minus 8 coulombs of charge is repelled from the thundercloud and accelerates downwards. Ignoring air resistance, calculate its kinetic energy as it lands. The particle's kinetic energy is going to come from a combination of its acceleration from the electric field, EQH, which is just EQD, but we've called the DH, and we're also going to have the energy that we've gained from the acceleration due to gravity, mgh. And so we've got the energy from the electric field and the energy from gravity. We can shorten this for our calculator by factorizing the height out. This is an optional step, but it just means you don't have to type in the height twice. Putting in our numbers gives me 9.828 or 9.8 joules to two significant figures. Calculate the final velocity of the raindrop. To find our final velocity, we can use our kinetic energy equation, solving that for velocity by doubling both sides, dividing both sides by the mass, and then square rooting. Putting in our numbers gives me 809.4 or 810 meters per second to two significant figures. If the thundercloud was to descend to half its original height, explain how the final velocity of the raindrop would be affected. The final kinetic energy is proportional to the height of the thundercloud, as we saw here when we factorized the height out. Therefore, halving the height halves the raindrop's final kinetic energy. This is because not only do we half the distance that it traveled through the electric field, we also half the distance it traveled through the gravitational field. The final velocity is proportional to the square root of its final kinetic energy, as we see in this equation here. We have our velocity proportional to the square root of our kinetic energy. Therefore, halving the final kinetic energy reduces the final velocity by a factor of the square root of 2. Because we know that our velocity is proportional, where this is the sign for proportional, to the square root of our kinetic energy, we know that if we instead have half our kinetic energy, we can rearrange this to be 1 over the square root of 2 multiplied by the square root of EK. This is something you can mathematically do, and so we can see that our velocity has decreased by a factor of the square root of 2. A weather balloon carrying a small electric charge drifts sideways beneath the thundercloud. Explain how its electric potential energy changes as it moves. The weather balloon moves perpendicular to the electric field lines, since we're told it drifts sideways, and it therefore does no work against the electrostatic force. It therefore experiences no change in its electric potential energy. Direct current. Question 1. Explain how the direction of conventional current relates to the flow of electrons. The conventional current is in the direction of positive charge flow, which is in the opposite direction to the flow of negative electrons. And so if we have electrons moving in one direction, we define the current in the opposite direction. This is due to historical reasons. Question 2. Calculate the amount of current flowing in the following situations. 170 coulombs of charge flow through a wire in 20 seconds. We know that current is charge over time. We know the charge, we know the time, which gives us 8.5 amps. 2,000 electrons pass through a resistor in 0.13 seconds. To find the charge, we take the charge of an electron and multiply it by 2,000. Doing so gives us 3.2 times 10 to the minus 16 coulombs. Putting that now into our current equation gives us 2.462 times 10 to the minus 15, or 2.5 times 10 to the minus 15 amps to two significant figures. Question 3. The amount of charge a battery can store is often rated in milliamp hours, or mAh. Explain what this unit represents. 1 milliamp hour refers to the amount of charge transferred in 1 hour by a current of 1 milliamp. So if we take our current equation, which is I is equal to Q over T, rearranging that for charge by multiplying both sides by T, if our current is 1 milliamp and our time is 1 hour, then as said in the above sentence, we get the amount of charge transferred by a milliamp of current in 1 hour. Question 4. Calculate the amount of charge stored in the following batteries. Our first battery has a charge of 2000 milliamp hours, and so our current is 2000 milliamps, which is 2 amps, and our time is 1 hour, which is 3600 seconds. Putting those numbers in gives me 7200 coulombs to two significant figures. And now it's important to note, we're not saying that this battery is actually capable of supplying this amount of current, just that the amount of charge it stores is equivalent to this amount. In our second example, we have a charge of 65 amp hours, and so we have a current of 65 amps and a time of 1 hour, or 3600 seconds. Knowing our charge equation, knowing our current and our time, gives me 2.34 times 10 to the 5, or 2.3 times 10 to the 5 coulombs to two significant figures. For our last battery, we have a charge of 1200 amp hours, corresponding to a current of 1200, and a time once again of 1 hour, or 3600 seconds. Putting our current and our time into our charge equation gives us 4.32 times 10 to the 6, or 4.3 times 10 to the 6 coulombs to two significant figures. Question 5. The Large Hadron Collider is a circular particle accelerator. It sends beams of protons around a circular track at nearly the speed of light. Each beam contains 2.8 times 10 to the 14 protons and travels around the track 11,000 times every second. Calculate the number of protons traveling around the track every second. Our number of protons is going to equal the protons per beam multiplied by the amount of times it circulates per second, which gives us 3.08 times 10 to the 18, or 3.1 times 10 to the 18 to two significant figures. Calculate the amount of charge traveling around the track every second. To find our amount of charge, we need to multiply the charge of the electron, which is the charge of a proton, except for a proton it's positive, by our number of protons traveling around per second. Putting those numbers in gives us 0.4928, or 0.49 coulombs to 2 significant figures. Calculate the total current produced by the circulating protons. Our current is charge over time, our charge is what we just found in part B, and our time is 1 second, since this charge is traveling around in 1 second, which gives us 0.4928, or 0.49 amps to 2 significant figures. Discuss 2 changes that could be made to the proton beam to increase this current. The current could be increased by either increasing the amount of protons, or by increasing the speed of the protons. And so going back to our current equation, we're saying that we could increase the amount of protons, which would increase the charge, or alternatively, we could increase their speed, which would decrease the time. Question 6. A lightning bolt delivers 25 coulombs of charge in 50 microseconds. Calculate the number of electrons transferred in the strike. Our charge is going to be our number of electrons multiplied by the charge of the electrons. Solving this for our n by dividing both sides by e, we know we have a charge of 25, and we know the charge of the electron, which gives us 1.563 times 10 to the 20, or 1.6 times 10 to the 20 to 2 significant figures. Calculate the average current. We know our time was 50 microseconds, which is 5 times 10 to the minus 5 seconds, since 50 microseconds is 50 times 10 to the minus 6, which equals 5 times 10 to the minus 5. We know our current is charge per time, where our charge was 25 coulombs, and we just found our time, which gives us 5.0 times 10 to the 5 amps. Calculate how much charge would flow in 10 microseconds at this current. A time of 10 microseconds equals 1 times 10 to the minus 5 seconds, since, once again, micro is times 10 to the minus 6. We know our current is charge over time, solving that for our charge by multiplying both sides by time, putting in our current and our time, gives us 5 coulombs. Voltage. Question 1. Calculate the voltage across the following electrical components. A lamp uses 12 joules of energy when a charge of 3 coulombs passes through it. Knowing that voltage is the change in energy per charge, our energy is 12, our charge is 3, which gives us 4 volts. A heater consumes 18 joules of energy after receiving 2.5 coulombs of charge. Once again, voltage is energy over charge, our energy is 18, and our charge is 2.5, which gives us 7.2 volts. Question 2. Calculate the energy supplied to the following electrical components. A phone charger supplies 0.8 coulombs of charge at 5 volts. Knowing that voltage is energy over charge, we can multiply both sides by charge to find that the energy is voltage times charge. Putting in our voltage and our charge gives us 4 joules. A 4.5 volt speaker uses 6.6 coulombs of charge. Knowing our voltage equation and rearranging as we did above, putting in our voltage and our charge gives us 29.7 or 30 joules to 2 significant figures. Question 3. Calculate the charge supplied to the following electrical components. A 12 volt car headlight consumes 300 joules of energy. Knowing our voltage equation, we can solve this for charge by swapping around our V and our Q. Putting in our energy and our voltage gives me 25 coulombs. An electric kettle running from a 240 volt outlet uses 4,600 joules of energy. Having our voltage equation, rearranging that for charge as we did in the last question, putting in our energy and our voltage gives me 19.17 or 19 coulombs to 2 significant figures. Question 4. A perimeter fence at a prehistoric wildlife sanctuary is charged with a voltage of 10,000 volts. Explain what this voltage rating tells us. The voltage rating tells us the joules of energy transferred by each coulomb of charge. For a 10,000 volt fence, each coulomb of charge delivers 10,000 joules of energy. And so, knowing our voltage equation, we know that is energy per charge, where 10,000 volts means an energy of 10,000 joules for each 1 coulomb of charge. An ill-advised visitor attempts to climb the fence and receives 0.0015 coulombs of charge. Calculate the energy transferred to the visitor. We know our voltage is the change in energy per charge. Multiplying both sides by charge to find the change in energy, putting in our charge and our voltage, gives us 15 joules. A section of fence develops a fault and is now only capable of delivering 5,000 volts. Calculate the charge this section must provide to transfer the same amount of energy. Knowing that voltage is energy per charge, we can swap our voltage and our charge around to find that charge is the change in energy per voltage. Putting in this same amount of energy, 15 joules, and our 5,000 volts, gives us 0.003 coulombs. Question 5. A defibrillator delivers a shock to a patient over a duration of 4.1 milliseconds. The shock transfers 360 joules of energy at a voltage of 820 volts. Calculate the amount of charge delivered to the patient. Knowing our voltage is energy per charge, we can rearrange that so that our charge is the change in energy per voltage. Our change in energy is 360 joules, our voltage is 820, which gives us 0.4390 or 0.44 coulombs to two significant figures. Calculate the average current supplied to the patient. Our time of 4.1 milliseconds is 4.1 times 10 to the minus 3 seconds. Knowing that current is charge per time, knowing our charge and our time, gives us 107.1 or 110 amps to two significant figures. Discuss how the quantity of charge delivered would change if the patient received the same energy at a higher voltage. Increasing the voltage increases the amount of energy carried by each charge. Less charges are therefore needed to transfer the same amount of energy. Mathematically, charge is change in energy per voltage. Therefore, increasing the voltage while keeping the energy delivered the same will result in a reduced amount of charge delivered. Circuits. Question 1. Determine the unknown current in the diagrams below. We have a voltage source in series with our ammeter with our unknown current, in series with a resistor, which is in series with another ammeter, this one reading 2.4 amps. Because this is a series circuit, the current has nowhere else to go, and so if we're reading 2.4 amps here, then we must be reading 2.4 amps there. In our second circuit, we have a voltage source, through which there is a current of 2.4 amps. The current splits into one branch with our resistor and unknown current, and another branch with another resistor, and a current of 1.8 amps. We know that our current of 2.4 amps splits into two at this junction, with this junction being 1.8 amps, which means that our other junction must have 0.6 amps to make up our total of 2.4 amps. Our third circuit has our unknown ammeter in series with a voltage supply. Our current splits into two parallel branches, one branch with a 1 amp ammeter and a resistor, and the other with a resistor and a 2 amp ammeter. And so our current is once again splitting at this junction. Because it splits into 1 amp and 2, our total current must be 3 amps. In our fourth circuit, we have a voltage source in series with a resistor and a 3 amp ammeter, as well as our unknown ammeter. The current splits through two resistors, and along our second branch, we have a 1.5 amp ammeter. This here is a little bit of a trick question, because we know we must have 3 amps flowing through here. That current must also flow through our unknown ammeter, and so our unknown current is just our 3 amps. In our fifth circuit, we have our voltage supply in series with a 12 amp ammeter. Our current splits into an ammeter and a resistor, and another ammeter reading 8.5 amps and another resistor. And so our 12 amps splits down this branch into 8.5 amps, and our unknown current, which is going to be 12 amps minus 8.5, which gives us 3.5 amps. In our sixth circuit, our voltage supply is in series with a resistor and an unknown ammeter. It splits into a 20 amp current and a resistor and a 13 amp current. Because our current splits into 20 amps and 13, that means our original current must be 33 amps. Question 2. Determine the unknown voltage in the diagrams below. We have a voltage source with 12 volts across it, in series with a resistor with our unknown voltage. Because there's 12 volts across our power supply, there must be 12 volts being used across the resistor. Another way to think of this is that if we have our probes here, and we measure 12 volts, then by just moving them along the wire, we shouldn't read anything different. And so if we move this probe over to here, and this probe over to here, we have just moved them along wire, and so we shouldn't be measuring anything different. Another way to think of this is that our 12 volt measurement here isn't just saying that the 12 volts is across this point and this point, it's saying that the voltage is across this entire branch and this entire branch. In our second circuit, our voltage source has 18 volts across it, we have a resistor with 10 volts across it, and another resistor with our unknown voltage. So we have our 18 volts, 10 of which is used across this resistor, which leaves 8 for our second resistor. For our third circuit, we have a voltage source with our unknown voltage across it, which is powering 3 resistors, with voltages of 2, 4, and 1 across them. Our total source voltage must therefore be the sum of these 3 voltages, which is 7 volts. Our fourth circuit has a voltage source with 2 volts across it, connected to 2 resistors in parallel, and we have 2 volts across this resistor as well, and an unknown voltage across our other resistor. Now, going back to what I was saying in our last explanation here, isn't just saying that the voltage of 2 is between these 2 points, it's saying that this voltage of 2 volts is across these entire branches. And so if you were to stick your probes anywhere along these branches, you would measure 2 volts, which means that our unknown voltage is 2 volts. For our fifth circuit, we have a voltage source, which is splitting across 2 parallel branches, one with a resistor receiving 5 volts, and the other with a resistor receiving our unknown voltage and a voltage of 2 volts. Because we know that we have a 5 volt difference across this resistor, we know we must have a 5 volt difference across these 2 resistors. They're in series, and so their voltages add together. Because we've already subtracted 2 for this resistor, what's remaining is our 3 volts. For our last circuit, we have a voltage source with 10 volts across it, in series with a resistor of 2 volts, which is connected in parallel to 2 resistors, one of which with our unknown voltage. And so we have our 10 volt source, which, because it's in series with our 2 volt resistor, the remaining voltage for these 2 resistors is only 8 volts. And so the voltage across this branch is going to be 8 volts. Question 3. Draw the symbols for the following components. The symbol for a battery is this symbol here. We might also join multiple of these together to show battery cells. The symbol for a resistor is just a rectangle. This is the British notation that New Zealand also follows. The Americans would draw them like this. The symbol for a lamp is just a circle with an X in it. We have an open switch through which current is not able to flow, and a closed switch through which current is. Question 4. Draw the following circuits in the boxes below. A battery connected in series with 2 resistors. We have our battery, and we have our 2 resistors connected in series. A lamp in series with a battery and a switch. Here we have our lamp in series with a battery and in series with a switch. 3 lamps and a battery connected in parallel. So we have our battery and our lamps, all of which are connected in parallel to each other, meaning that the current splits at each junction. A battery powering a lamp with a voltmeter measuring the voltage across the lamp. We have our battery powering our lamp, and to measure the voltage, we must have probes either side. 2 resistors and a battery in parallel. An ammeter measures the current through the battery. We have our battery, and to measure the current through the battery, our ammeter must be in series with it. Our battery is in parallel with our two resistors. A resistor, lamp, and battery in series, and a voltmeter measures the voltage across the resistor. We have our resistor, lamp, and voltage source in series, and a voltmeter measuring the voltage across the resistor. Question 5. Draw an arrow on the circuit below to show the direction of the conventional current. Here we have our circuit, and we have our positive plate on this side, which is always the longest side, and the negative plate on this side. We know that the conventional current is the direction of positive charge flow. Our positive charges are starting at this terminal here, and they are moving to the negative terminal. So this is the direction of our conventional current. Ohm's law. Question 1. Calculate the unknown voltage in the diagrams below. In this diagram here, we have a voltage source in series with an ammeter measuring 5 amps and a 1.8 ohm resistor with our voltmeter across it. Ohm's law tells us that the voltage is the current through the resistor, which we know is 5 amps. Because this is a series circuit, that means our 5 amps must flow through just one path. And we multiply that by our resistance, 1.8. Putting those numbers in gives us 9 volts. In our next circuit, we have our voltage source, our ammeter now measuring 2.5 amps, all in series with a 22 ohm resistor. Across this resistor, we have our voltmeter. Once again, we know that V is equal to IR, where I is the current through our resistor, which once again, because this is a series circuit, is our 2.5 amps, and our resistance is 22 ohms, which gives us 55 volts. And finally, in our last circuit, we have our voltage source, which is connected to a 550 ohm resistor, in parallel with another 12 kilo ohm resistor, and an ammeter measuring 15 milliamps. Our voltmeter is across our 12 kilo ohm resistor. And note that our 15 milliamp current is 0.15 amps, and our 12 kilo ohm resistance is 12,000 ohms. The voltage across our resistor is going to be the current through the resistor, which is our 15 milliamps, because we know that 15 milliamps is passing through this branch, and this is the branch with this resistor. Our resistance is of course just our 12 kilo ohms, where our 550 ohms is just a red herring. We don't need it. Putting these numbers in gives me 180 volts. Question 2. Calculate the unknown current in the diagrams below. In this circuit, we have a 12 volt source in series with our unknown current and a 470 ohm resistor. Now, just as we know that V is equal to IR, we can rearrange that for current by dividing both sides by the resistance, which gives us that I is equal to V over R. Using that equation, putting in our voltage and our resistance, gives me 0.02553 or 0.26 amps to two significant figures. For our next circuit, we have a 3 volt voltage source in series with a 1 kilo ohm resistor and our unknown ammeter, where our current of 1 kilo ohms is just 1000 ohms. Once again, using our equation that the current is voltage over resistance, putting in our voltage and our resistance gives me 0.0030 amps. For our last circuit, we have a 6 volt supply connected to a 180 ohm resistor in parallel with a 120 ohm resistor and our unknown ammeter. We once again know that current is voltage over resistance, where we know that our current here is the same as our current through the 120 ohm resistor. And so if we have a resistance of 120 ohms, we just need to put in our voltage. Now we have our voltage source of 6 volts, which tells us that the voltage between this entire section and this entire section is 6 volts. Which means that the voltage across our 120 ohm resistor is 6 volts, as is the voltage across our 180 ohm resistor. So that gives us 6 over 120, or 0.050 amps. Question 3. A company saves money by using 0.82 ohm aluminium cables instead of more expensive 0.5 ohm copper cables. The cables deliver power at a voltage of 5.5 volts to a 1.2 ohm device. Describe how the resistance of a cable affects the current flowing through it. Resistance is the opposition to current. For the same amount of voltage applied, an increase in resistance will result in a proportional decrease in current. So going back to our equation here, if we have the same amount of voltage, an increase in the resistance will result in a proportional decrease in current. Calculate the current flowing through the copper cable. Our copper cable has a resistance of 0.5 ohms, and our device has a resistance of 1.2 ohms. Across these is a voltage of 5.5 volts. And so our resistance is the sum of these resistances, which is 1.7 ohms. And now knowing that V is equal to IR, and therefore I is equal to V over R, we put in our voltage of 5.5, our total resistance of 1.7, which gives us 3.235, or 3.2 amps to two significant figures. Calculate the voltage needed across the aluminium cable to achieve the same current. Our total resistance is now the resistance of our device, 1.2, but now added to that is the increased resistance of our aluminium cable, 0.82 ohms, which gives us 2.02 ohms. Once again, knowing that V is equal to IR, where the current is the current that we found in the last question, since we're calculating the voltage needed for the same amount of current, and our resistance is our 2.02. Which is the resistance with our aluminium cable. Putting those numbers in gives me 6.535 or 6.5 volts to two significant figures. Question 4. Amos is replacing the battery on his Corvette. The new battery has a terminal voltage of 12 volts. Amos places a hand on each terminal to lift the battery. If the resistance between his hands is 1.3 million ohms, calculate the resulting current. Our resistance of 1.3 mega ohms is 1.3 times 10 to the 6 ohms. We know that V is equal to IR, rearranging that for current, putting in our voltage of 12 and our resistance between his hands, gives us 9.231 times 10 to the minus 6, or 9.2 times 10 to the minus 6 amps to two significant figures. Amos later gets cryofluid on his hands, lowering the resistance between them to 270 kiloohms. Calculate the current that would flow between his hands if he lifted the battery once more. Our resistance of 270 kiloohms is 2.7 times 10 to the 5 ohms. Once again, V is equal to IR, and so I is equal to V over R, putting in our same voltage with our new resistance, gives us 4.444 times 10 to the minus 5, or 4.4 times 10 to the minus 5 ohms to two significant figures. Humans can typically detect currents as low as 1 milliamp. Calculate the voltage required to achieve this current for each of the above examples. Our current of 1 milliamp is 1 times 10 to the minus 3 amps. For our resistance of 1.3 mega ohms, using our V equals IR, where our current is our 1 milliamp, and our resistance of 1.3 mega ohms is 1.3 times 10 to the 6, which gives us 1300 volts. Repeating this for our second resistance gives us 270 volts. Equivalent resistance. Question 1. Write an equation for the equivalent resistance in parallel, solved for RT. This is our equation for the resistance in parallel. To solve this for our total resistance R, we can first multiply both sides by R, and then divide both sides by the brackets and swap the sides around. Question 2. Calculate the equivalent resistance of the following resistor combinations. In our first example, we have a 360 ohm resistor in series with a 140 ohm resistor. Series resistances add, and so the result is 500 ohms. For our second example, we have a 20 ohm, 30 ohm, 10 ohm, and another 10 ohm resistor, all of which are in series. Once again, series resistances add, which gives us 70 ohms. For our third example, we have a 20 kilo ohm resistor in parallel with a 15 kilo ohm resistor. Using the equation we found up here, gives us that the total resistance is 1 over our first resistance plus 1 over our second resistance, which gives us 8,571 or 8,600 ohms to two significant figures. For our last example, we have an 8, 4 and 2 kilo ohm resistor, all of which are in parallel. Once again, using this equation up here, this time for 3 resistances, our total resistance is 1 over the sum of our 1 over resistances, which gives us 1.143 or 1.1 ohms to two significant figures. Question 3. Explain why equivalent resistance goes down when another resistor is added in parallel. When a resistor is added in parallel, another pathway is added through which more current can flow. Since more current is able to flow, the overall resistance of the circuit must have decreased, meaning that if we add a resistor in parallel, even though we've added a resistor, more importantly, we've added a pathway, and it doesn't matter how bad this pathway is, it still counts as another pathway or another hole in the bucket, meaning that current can flow down this path that previously couldn't flow before, and so we must have more current flowing, which means we must have less resistance. Question 4. Calculate the unknown resistance in the diagrams below. We have a total resistance of 10, and we have 2 resistors in series, one of which is our unknown, and the other is 4. We know that resistors add in series, and so our 10 ohms is our total, which is going to be the sum of our 2 resistances, one of which being 4, and the other our unknown. Solving this for our unknown by subtracting 4 from both sides gives us 6 ohms. For our second example, we have a total resistance of 3 kilo ohms, and we have 2 resistors in parallel, one of which is our unknown, and the other is 10 kilo ohms. We know that 1 over the total resistance is equal to the sum of our 1 over resistances, solving that for R1 by first subtracting 1 over R2 from both sides, as well as swapping the sides around, and then we can take the inverse of both sides. Putting our numbers in gives me 4,286 or 4,300 ohms to two significant figures. For our third example, we have a total resistance of 1 mega ohm, and we have 3 resistances, a 350 kilo ohm, a 250 kilo ohm, and our unknown resistance. Resistors in series add, and so our total resistance, 1 mega ohm, or 1 times 10 to the 6, is equal to the sum of our 3 resistances. We can solve this for our unknown by subtracting our known resistances from both sides, which gives us 4.0 times 10 to the 5 ohms. For our fourth example, our total resistance is 30 ohms, and we have 3 resistors in parallel. One is 200 ohms, the other is 100, and our third is our unknown. For resistors in parallel, the 1 over our total resistance is the sum of our 1 over resistances. Solving this for our unknown resistance, we can first subtract 1 over 200 and 1 over 100 from both sides and swap them around, and then take the inverse of both sides, which gives us 54.55 or 55 ohms to two significant figures. In our fifth example, our total resistance is 45 ohms, and we have a 35 ohm resistor, a 7 ohm resistor, and our unknown resistor, all in series. Series resistances add, so we know that 45 is equal to 35 plus 7 plus our unknown resistance. Solving this for our unknown by subtracting 35 and 7 from both sides and swapping them around, which gives us 3 ohms. For our last example, we have a total resistance of 540 ohms, and we have 3 resistors in parallel, a 2 kilo ohm, a 3 kilo ohm, as well as our unknown. We know 1 over our total resistance is the sum of our 1 over resistances, solving this for our unknown resistance by subtracting 1 over 2000 and 1 over 3000 from both sides. Taking the inverse of both sides gives me 9818 or 9800 ohms to two significant figures. Question 5. Calculate the equivalent resistance of the following resistor combinations. We have a 2 ohm and a 5 ohm resistor in series with each other, in parallel with a 10 ohm resistor. So essentially we have two branches in parallel, and so we use the parallel resistance equation. 1 over the total resistance is the sum over our 1 over resistances, where one branch has a 2 and 5 in series, and so we add those resistances together, and our other branch just has 10. Taking the inverse of both sides and combining our 2 and 5 into 7, we get 4.118, or 4.1 ohms to two significant figures. In our next example, we have a 15 ohm resistor in series with a parallel branch containing a 12 and 6 ohm resistor in parallel with each other. So we essentially have two things in series, and series resistances add. So we have our total resistance is our first object in series, which is our 15 ohm resistor, and the next object is our parallel branch. And because the total resistance of this branch can be given by 1 over the total resistance is 1 over 12 plus 1 over 6. Solving that for our R, we take the inverse of both sides, which gives us 1 over 12 plus 1 over 6, which we have here. That gives us 19 ohms. For our next circuit, we have a 2 kilo ohm and 3 kilo ohm resistor in series with each other, which is in parallel with another branch containing a 2 kilo ohm and 8 kilo ohm in series. So we have two parallel objects, so our resistance is 1 over the resistance of the first branch plus 1 over the resistance of the second branch. The first branch has our 2000 and our 3000 in series, and so these resistances add together, and the second branch has our 2000 and 8000, and because they're once again in series, they once again add together, which gives us 1 over 5000 plus 1 over 10,000. Taking the inverse of both sides gives me 3333, or 3300 ohms to two significant figures. For our next circuit, we have a 25 ohm resistor in parallel with a 15 and 5 ohm resistor in series, and also in parallel with a 10 ohm resistor. Because this is three objects in parallel, our 1 over total resistance is the sum of our 1 over resistances of each branch. The first branch is 25, the second branch is 15 plus 5 since they're in series, and the last branch is 10. Taking the inverse of both sides gives me 5.263, or 5.3 ohms to two significant figures. For our next circuit, we have a 5 ohm resistor in series with this parallel structure containing a 20 ohm on one branch and a 30 and 10 ohm resistor on the other. So we have these two objects in series, and our series resistances add. So our total resistance is our first object, our 5 ohms, plus our parallel branch, and using this same system that we used above, our parallel branch resistance is 1 over the sum of our 1 over resistances. On the first branch, that's 20, so we have 1 over 20, and on the second branch, it's 30 plus 10, so we have 1 over 30 plus 10. That gives me 18.33, or 18 ohms to two significant figures. Lastly, we have a 2 and 13 ohm resistor in parallel with each other, which is in series with a 4 and 3 ohm resistor, also in parallel with each other. Since we have two structures in series, these structures' resistances add together, and because they're in parallel, we get them by going 1 over the sum of their 1 over resistances. And so for our first branch, that's 1 over 2 ohms plus 1 over 13 ohms, and for our second branch, it's 1 over 4 ohms plus 1 over 3 ohms, which gives us 3.448, or 3.4 ohms to two significant figures. Question 6. Calculate the unknown resistance in the diagrams below. Our total resistance is 750 ohms, and we have a 700 ohm and 300 ohm resistor in series, which are in parallel with our unknown resistance. These two branches are in parallel, so we know that 1 over our total resistance is the sum of our 1 over resistances of each branch. The first branch has a 700 and 300 in series, and the second branch just contains our unknown. We can solve this for our unknown by first subtracting our 1 over 700 plus 300 from both sides, which is 1 over 1000. We can then take the inverse of both sides, which gives me 3000 ohms. In our next circuit, we have a total resistance of 6, and we have two 2 ohm resistors in parallel, which are in series with our unknown resistance. So we have two structures in series, and so our resistances add. So our 6 ohms, our total resistance, is the sum of the resistance of our parallel branch, which is 1 over 1 over 2 plus 1 over 2, plus our unknown resistance. Rearranging that for our unknown resistance by subtracting our 1 over 1 over 2 plus 1 over 2 from both sides, which gives me 5 ohms. In our next circuit, we have a total resistance of 4, and we have a 5 and 1 ohm resistor in series, which are in parallel with another branch containing a 4 ohm resistor and an unknown resistance. Because we have two branches in parallel, 1 over our total of 4 is equal to the sum of our 1 over resistances of each branch. Our first branch contains a 5 and 1 ohm resistor in series, so they add together, and our second branch contains our 4 and our unknown, which are in series, so they once again add together. We can solve this for our unknown by first subtracting our 1 over 5 plus 1 from both sides, which is 1 over 6. We can then take the inverse of both sides and then subtract 4 from both sides, which gives me 8 ohms. In our last circuit, we have a total resistance of 2 ohms, and we have a unknown resistance and a 2 ohm resistor in parallel, which are in series with a 2 and 1 ohm resistor, once again in parallel. We have these two structures in series, and so their resistances add together. So our total of 2 is equal to the resistance of these two parallel branches added together. Their resistance is 1 over our unknown plus 1 over 2, plus 1 over 2 plus 1 over our 1 ohm. We can solve this for our unknown by first subtracting this from both sides, taking the inverse of both sides, subtracting our half from both sides, and then once again taking the inverse, which gives us 4 ohms. Question 7. Calculate the total current flowing through the circuits below. We have our ammeter, we have our 12 volt source, that's in parallel with a 200 ohm resistor, which is once again in parallel with a 180 and 40 ohm resistor in series with each other. And now to find the current flowing, we must first find the total resistance. Our total resistance, because we have two branches in parallel, is 1 over the sum of our 1 over resistances, which is 1 over 200, plus 1 over our 2 in series, 180 plus 40, which gives us 104.8 ohms. Now we know that V is equal to IR, which means that I is equal to V over R. We know that our voltage is 12. We just found our resistance, which gives us 0.1145 or 0.11 amps to two significant figures. In our next circuit, we have our unknown ammeter, our 9 volt source. This is in series with a 20 ohm resistor and a 25 and 30 ohm resistor in parallel. These two are in series, and so their resistances add together, and so our total resistance is our 1 over the sum of our 1 over resistances for our parallel branch, and then just added with our 20, which gives me 33.64 ohms. Once again using V equals IR, solving that for our current, putting in our voltage and our resistance, gives me 0.2675, or 0.27 amps to two significant figures. Power. Question 1. Calculate the power in the following situations. An electric fan is connected to 240 volts and consumes 0.41 amps of current. We know that P is equal to IV, we know our I, we know our V, which gives us 9.84 or 9.8 watts to two significant figures. A solar panel outputs 8 amps at a voltage of 35 volts. Once again, P is equal to IV, our current is 8, our voltage is 35, which gives us 280 watts to two significant figures. Question 2. Calculate the current produced in the following situations. A desktop computer uses 120 watts of power at a voltage of 240 volts. We know that P is equal to IV, rearranging that for current by dividing both sides by voltage, we know our power, we know our voltage, which gives me 0.5 amps. A Bluetooth speaker is powered from a 5-volt battery and consumes 20 watts of power. We know that P is equal to IV and I is equal to P over V. We know our power, we know our voltage, and so that gives us 4 amps. Question 3. Calculate the voltage supplied in the following situations. An e-scooter battery provides 12 amps of current and delivers 650 watts of power. Knowing that P is equal to IV, we can rearrange this for voltage by dividing both sides by current. We know the power, we know the current, and so we get 54.17 or 54 volts to 2 significant figures. A camera flash briefly draws 90 watts of power with a current of 4,500 milliamps. 4,500 milliamps is just 4.5 amps, since milli is times 10 to the minus 3. We know that P is equal to IV, we know that V is equal to P over I, our power is 90, our current is 4.5, which gives us 20 volts. Question 4. In New Zealand homes, electricity is supplied at 240 volts. A standard wall outlet is able to deliver a maximum current of 16 amps before the circuit breaker interrupts the circuit. Calculate the current drawn by a 2000 watt heater. We know that power is current times voltage, and we can rearrange this for current by dividing both sides by voltage. We know our power, and we know our voltage, which gives me 8.333 or 8.3 amps to 2 significant figures. A multi-plug is used to connect both the heater and a 1900 watt toaster to a single wall outlet. Use calculations to determine if this will activate the circuit breaker. Knowing that our maximum current is 16 amps before the circuit breaker trips, we just need to find our current like we did in the last question, where we know our voltage, and our power in this case is both the power of our heater as well as the power of our toaster, which is 3,900 watts. Putting that in gives us 16.25 amps. 16.25 is greater than our 16 amps, and so yes, our circuit breaker will activate. A cold and hungry homeowner discovers a way to disable the circuit breaker. Explain the risks associated with this action. Electrical wiring in a home is designed to dissipate a particular amount of heat. If more current than is intended passes through it, it may generate more heat than it can dissipate, causing unsafe temperatures. This could cause damage to the wiring and increase the risk of a fire occurring. If 16 amps of current is delivered to the appliance through a 0.1 ohm cable, calculate how much energy the cable dissipates as heat in 30 seconds. We can use the equation that P is equal to I squared R, which is an equation we get by taking P equals IV and knowing that V is equal to IR, replacing our V with IR. I times I is I squared, and hence I squared R. We know our current, and we know our resistance, which gives us 46.08 watts. And now to take this power and find our energy, we can use power equals change in energy over time, rearranging this for energy by multiplying both sides by the time, putting in our numbers, which gives me 1382 or 1400 joules to 2 significant figures. Question 5. A high school chemistry teacher parks his RV and accidentally leaves its two 55 watt headlights on. The RV's battery stores 200 amp hours of charge at a voltage of 24 volts. Calculate the charge stored in the battery in coulombs. And so our 200 amp hours is a measurement of charge, which is equivalent to the amount of amps that would be supplied in an hour. We can convert this to coulombs, knowing that current is charge over time. We can solve for charge by multiplying both sides by time, putting in our 200 amps, and our 1 hour, or 3,600 seconds, gives us 7.2 times 10 to the 5 coulombs. Calculate the current drawn by each headlight. Since we know our power and our voltage, we can find the current using P equals IV, solving this for current by dividing both sides by V, putting in our power and our voltage, gives me 2.292 or 2.3 amps to 2 significant figures. Calculate the time it will take for the RV's battery to fully discharge. We know the amount of current and we know the amount of charge, and so to find the time, we can use that current is charge over time, rearranging this for time by swapping the I and T around, which is something you can mathematically do, putting in our charge and our current for one headlight, multiplied by 2 since there are 2, gives us 1.571 times 10 to the 5, or 1.6 times 10 to the 5 seconds to two significant figures. Question 6. A time-traveling sports car uses a lightning rod to charge its capacitor. A typical lightning strike has a voltage of 300 million volts. The sports car requires 1.2 times 10 to the 9 watts of power. Calculate the current the lightning strike must provide to deliver this amount of power. 300 million volts is 3 times 10 to the 8 volts. And now to find our current, since we know our voltage and our power, we can use P equals IV, solving for current by dividing both sides by voltage, putting in our power and our voltage, gives me 4 amps. It takes 12 seconds for the car to accelerate to the speed required for time travel. Calculate the energy transferred to the car during this time. Knowing our power and our time, we can use that power as the change in energy per time, rearranging that for our change in energy by multiplying both sides by our time, putting in our power and our time, gives me 1.44 times 10 to the 10, or 1.4 times 10 to the 10 joules to two significant figures. Question 7. A 3.1 volt digital watch battery with a charge capacity of 60 milliamp hours is advertised to last 7 years. Calculate the average current the battery would supply over this time. Our charge of 60 milliamp hours is equivalent to the amount of charge transferred by 60 milliamps over a duration of an hour or 3,600 seconds, which is equivalent to 216 coulombs. And our time of 7 years is 7 times 365 days times 24 hours times 3,600 seconds, which gives us 2.208 times 10 to the 8 seconds. And now to find our current, we can use the fact that current is charge over time. We know our charge and we know our time, which gives us 9.783 times 10 to the minus 7, or 9.8 times 10 to the minus 7 amps to two significant figures. Calculate the energy supplied by the battery. To do this, we first need to find our power, which we can find knowing the current and the voltage. The current we found in the last question, and the voltage we were given in the question. That gives us 3.033 times 10 to the minus 6 watts, which we can now use in our power equals change in energy over time equation, rearranged for energy by multiplying both sides by the time, putting in our power and our time, gives me 669.7 or 670 joules to two significant figures. A rechargeable battery of the same capacity is charged from empty using an average current of 15 milliamps. Calculate the time it will take to fully charge. Our current of 15 milliamps is 0.015 amps, since milli is times 10 to the minus 3. Knowing our current and knowing that it's the same capacity, which means it has the same amount of charge, we can find our time using current as charge over time, rearranging for time by swapping our current and our time around. Putting in our charge and our current gives me 1.44 times 10 to the 4, or 1.4 times 10 to the 4 seconds to two significant figures. Potential divider. Question 1. Calculate the unknown voltage in the diagrams below. We have a 12 volt source connected in series to a 20 and 40 ohm resistor, and our unknown voltage over our 20 ohm resistor. To find the voltage across this resistor, we can use the fact that V is equal to IR, where we know our resistance, that is our 20, but we don't know our current. Since this is a series circuit, we know that the total current in the circuit is also going to be the current through the 20 ohm resistor. And so to find this circuit current, we can use the fact that the total circuit current is the total circuit voltage divided by the total circuit resistance, which is just V equals IR, rearranged for I. Our total resistance, because this is a series circuit, is just the sum of our 20 and 40 ohms, which is 60 ohms, and our voltage was 12. So putting those numbers in gives us 0.2 amps. Putting that into our V equals IR equation gives us 4 volts. In our next circuit, we have a 240 volt source connected in series to a 47 and 23 kilo ohm resistor. Our unknown voltage is across the 47 kilo ohm resistor. For this question, our process is going to be much the same, where we're going to use V equals IR, where we know the resistance. However, we need to find the current, knowing that current is total voltage over total resistance. And once again, because this is a series circuit, the current flowing through the circuit is also the current flowing through the 47 kilo ohm resistor. Our voltmeter is not part of this circuit. The current does not flow through the voltmeter. We can find our total resistance, noting that this is a series circuit, so our resistances sum together to give us 70,000 ohms. Putting in our voltage and our total resistance gives me 3.429 times 10 to the minus 3 amps. Putting that into our V equals IR equation gives us 160.7 or 160 volts to two significant figures. Question 2. Calculate the unknown resistance in the diagrams below. We have a 16 volt source connected in series with our unknown resistance, over which there is a 4 volt drop, and a 3 kilo ohm resistor. To find our unknown resistance, we can use the fact that resistance is V over I, which is V equals IR rearranged. We know the voltage, but we don't know the circuit current. But because this is a series circuit, we can find the current at any point in this circuit, and it will be the same current that flows through our unknown resistance. Knowing that, we can determine the current flowing through our 3 kilo ohm resistor. We can use the fact that I is V over R, where we know the resistance, and we can easily figure out the voltage because the total circuit voltage is 16 volts, and we know that 4 of that drops over this resistor. What's left must be 12 volts, and so the voltage across this resistor is 12 volts, which gives us 0.004 amps. Putting that into our resistance equation gives me 1000 ohms. For our next circuit, we have a voltage source of 20 volts connected in series to our unknown resistance and a 240 ohm resistor, over which there is a 14 volt drop. Using a similar process to the previous question, we know that the resistance is voltage over current, where we can figure out the voltage since we have a 20 volt supply and 14 of it drops over our 240 ohm resistor. What's left is 6 volts. And so we have our voltage, and to find our current, we can look at the current through our 240 ohm resistor. Since the current through this resistor is the same as the current through our unknown resistance, because this is a series circuit. So we can use that current is voltage over resistance, where our voltage is 14 and our resistance is 240, which gives us 0.05833 amps. Putting that into our resistance equation gives me 10.29 or 10 ohms to two significant figures. Question 3. An appliance is connected to the output of a potential divider circuit. Discuss how the voltage supplied to the appliance changes as current flows through it. When the appliance is connected, an additional pathway for current is created. This decreases the total circuit resistance, increasing the total circuit current. Since we know that V is equal to IR, if our voltage stays the same, and we decrease the resistance by adding another pathway, then we increase the current. As the current through the series resistor has increased, it consumes more of the supply voltage. And so if we once again apply V equals IR, but this time to our series resistor, its resistance stays the same because it's a property of that component. And so if the current through it increases, then so too must the voltage it consumes. This leaves less voltage to be consumed across the parallel branch, reducing the voltage supplied to the appliance. And so, as we know in series circuits, our voltage is shared between the components. That means that if one is taking up more voltage, then less is left over for the others. Question 4. Carl designs a circuit to heat his bicycle seat. Two resistors are connected in series to an 18 volt battery as shown below. Calculate the current in the circuit. To find our current, we can take V equals IR and rearrange that for current. We know our voltage, but we don't know our resistance. We do know, however, that it's a series circuit, and our resistances add together, which gives us 160 ohms. Putting that number in gives us 0.1125, or 0.11 amps to two significant figures. Show that the voltage across the 40 ohm resistor is 4.5 volts. Knowing that V equals IR, we know the current through the resistor, and we know its resistance, which gives us 4.5 volts. Carl connects a lamp in parallel across the 40 ohm resistor as shown below. The lamp has a resistance of 80 ohms and requires 4.5 volts to operate normally. Use calculations to explain why the lamp will not operate correctly when connected this way. When the lamp is connected, the circuit resistance decreases and more current flows through the circuit. Because we've added an additional pathway for current to flow, our circuit resistance has decreased. This increases the voltage consumed by the 120 ohm resistor. Since there's now an increased current through this resistor, it's also consuming more voltage, and reduces the voltage consumed across the lamp and the 40 ohm resistor. And so this 18 volts has to be shared across this 120 ohm drop and the drop across this parallel branch. If this is using more, then this is using less. And now to use calculations to back up our statement, we know that the lamp requires 4.5 volts, so we just need to calculate the voltage across it. To do this, we can find the voltage across our 120 ohm resistor and then subtract it from our 18 volts. Our voltage across this resistor is just going to be the circuit current times its resistance of 120, since V equals IR. And while we know the 120, we don't know the circuit current. To find the circuit current, we can use the fact that it's equal to the total circuit voltage divided by the total circuit resistance, where we know that the total circuit voltage is 18, and we just need to find the total circuit resistance. To do that, we know that that is going to be the resistance of our parallel branch, which is going to be 1 over our 40 plus 1 over our 80, since this is how parallel resistors combine, and then because this is in series with our 120 ohms, we just add that on, which gives us 146.7. Putting that into our equation gives us 0.1227 amps. Using that in our voltage of 120 equation, we get 14.72 volts, which means that the voltage across the lamp is going to be our total voltage of 18 minus the voltage of our 120 ohm resistor, which gives us 3.28 volts. Therefore, the lamp voltage is now 3.28 volts, which is less than the 4.5 volts it requires. Lamp circuits. Question 1. Explain which electrical quantity provides the best measure of a lamp's brightness. Power is the best measure of a lamp's brightness. It represents the rate at which a lamp converts electrical energy to light and heat energy. Increasing the power increases the amount of electrical energy converted into light energy, which increases the brightness of the lamp. Question 2. 3 identical bulbs are connected to a voltage supply in the circuit shown below. So we have our voltage supply connected with 2 parallel branches, one of which containing 1 bulb and the other containing 2. Explain any difference in the brightness of bulbs 1 and 2. The branch containing bulb 1 has half the resistance of the branch containing bulb 2 and 3. As the voltage across the branches is the same, and V equals IR, the current and therefore power through bulb 1 must be double that of bulb 2. Bulb 1 will therefore glow twice as bright as bulb 2. And so because we have our power supply here, we know that the voltage across this branch and this branch must be the same, and so we have the same voltage drop across this bulb as we do across these 2 bulbs. However, because the bulbs are identical and we have 2 bulbs on this branch, that means we have double the resistance. Knowing that V is equal to IR, if our voltage is the same and we double our resistance, then we must halve our current, which means that half the current flows through our bulb 2 and 3, which means they are half as bright. Bulb 3 blows, stopping current from flowing through it. Explain how this affects the brightness of bulb 1. When bulb 3 blows, no current flows through the bulb 2 and bulb 3 branch. All the current now flows through the bulb 1 branch instead of 2/3 of it. Because this bottom branch here had double the resistance, that means we had 2/3 flowing through this branch and 1/3 flowing through this branch. With this branch now out of action, that means we now have 3/3, or in other words, the entirety of the current. As P is equal to IV and the voltage across the branch is unchanged, this 1/3 increase in current results in a 1/3 increase in power and therefore brightness. In other words, this equation here tells us that power and current are proportional, so that a 1/3 increase in current results in a 1/3 increase in power. If the fault was instead to create a short circuit across bulb 3, allowing current to flow with negligible resistance, explain how this would affect the comparative brightness of the bulbs. If bulb 3 develops a short, it no longer contributes to the resistance of that branch. Both branches will now have the same resistance, and since the voltage across the branches is the same, the current through each branch is the same. As P is equal to IV, the power and therefore brightness of bulb 1 and bulb 2 will be the same. In other words, if our bulb 3 is taken out of action, but current can still flow through it, then essentially we just have our two branches with identical bulbs. Because the branches are identical, so are their current, and so is their voltage, and so too is their power, and therefore so too is their brightness. Non-ohmic conductors. Question 1. Explain the difference between an ohmic and non-ohmic conductor. An ohmic conductor has a constant resistance and a linear relationship between voltage and current. A non-ohmic conductor has a variable resistance and a non-linear relationship between voltage and current, meaning that if we were to graph voltage and current, for a ohmic conductor we're going to have a straight line linear relationship, whereas for a non-ohmic conductor we're going to have a curved relationship. Question 2. Identify whether the graphs below represent an ohmic or non-ohmic conductor. Looking at our four relationships, ohmic conductors are where we have a linear relationship, and so our first one is ohmic, and our next three are curves, meaning that they are non-linear relationships, and so they must all be non-ohmic. Question 3. Marco investigates the relationship between the voltage and current across a bulb. Plot Marco's data on the graph below. And so we have our data, our voltage and our current, and we are to plot it on this graph of current versus voltage. Plotting those points, we get a nice curve. Explain how the shape of the graph indicates that the bulb is a non-ohmic conductor. The graph is non-linear, meaning that it's a curve, and shows smaller increases in current for each increase in voltage. This represents an increasing resistance, meaning that for each increase in voltage, we are getting less and less of an increase in current. Explain why the current through the bulb does not increase linearly with voltage. As the current and voltage supplied to the bulb is increased, the temperature of the bulb increases, which increases the resistance of the bulb. As V is equal to IR and R is not constant, the relationship between current and voltage is not linear. And so a bulb is a classic example of a non-ohmic conductor. As our voltage increases and we try to pass an increasing current through the bulb, because this increases the temperature of the bulb, it also increases the resistance and makes it harder and harder for the current to pass through. And so, as we see in this graph here, we get smaller and smaller increases in current. Magnetism. Question 1. What direction do electric field lines point? That is, away from north and towards south. This is something that you need to memorize. Question 2. Draw an N and S to indicate the unknown poles on the magnets below. Looking at our first example, we know that the field lines point away from north, and so this must be our north, and we know they point towards south, which means that this pole must be south. For our second example, knowing that our field lines point away from north means that this must be our north, and knowing they point towards south means that this must be our south. Question 3. Draw arrows on the diagrams below to show the direction of the magnetic field lines. We have our magnet here, and we have our field lines. Our arrows must point away from north and towards south. And with our horseshoe magnet here, once again, our arrows must point away from north and towards south. Question 4. Sketch the magnetic field around the bar magnet shown below. Our field lines are going to once again point away from north and towards south, and they're going to look something like this. Domain theory. Question 1. Discuss how the alignment of magnetic domains affects a material's overall magnetic field. When magnetic domains are aligned, their magnetic fields combine to create an overall magnetic field. When magnetic domains are not aligned, their magnetic fields oppose, reducing the overall magnetic field. If we are to imagine a material that can be magnetized, sections within this material behave like their own individual magnets, pointing in individual directions. If all of these so-called domains are not aligned, then the fields tend to oppose each other, cancelling out the overall magnetic field. However, if you were to align all of these domains together, their effects would instead combine and result in an overall magnetic field. Question 2. A bar magnet is cut in half as shown below. Use domain theory to explain why each half will still have both a north and south pole. When the magnet is cut in half, both halves have domains that point in the same direction as before. They therefore each still have a north and south pole on each end. Going back to our domain example here, if we were to cut this magnet in half, then essentially we now have two materials which still have domains pointing in the same direction, and each piece is still going to have a north and south pole. Question 3. A nuclear physicist drops his flathead screwdriver and notices the magnetized tip is now weaker. Use domain theory to explain why this has occurred. Before the screwdriver is dropped, the magnetized tip's magnetic domains aligned to create an overall magnetic field. When the screwdriver is dropped, the magnetic domains are knocked out of alignment, causing the overall magnetic field to become weaker. The idea being that we have a material which initially has the domains all in the same direction, but by giving it a knock, these domains will come slightly out of alignment, and so they'll start to cancel each other out and result in a weaker overall magnetic field. Discuss what the physicist could do to remagnetize the screwdriver tip. To remagnetize the screwdriver tip, the magnetic domains must be realigned. This can be done by bringing the screwdriver into another magnetic field, which will cause the magnetic domains to align to this field, resulting in an overall magnetic field again. And so if we were to bring a magnet nearby to our magnetic domains, that is going to cause our domains to align once again. Field around a current. Question 1. Explain how the direction of current flow in a wire can be used to determine the direction of the magnetic field encircling it. The right-hand grip rule can be used to determine the direction of a magnetic field encircling a current. Using your right hand and pointing your thumb in the direction of the current flow, your fingers will curl in the direction of the encircling magnetic field, as we're about to demonstrate in some of the examples below. Question 2. The diagrams below show current-carrying wires encircled by magnetic fields. By considering the magnetic field patterns around the wires, draw an arrow to show the direction of the current in each wire. And so we have our magnetic field indicated by these dots and X's, where the dots indicate out of the page and the X's indicate into the page. Think of this like an arrow, where if you see this, you have the arrow coming towards you, where the arrow is something like this, and you're viewing it from this angle here. Whereas if you see the X pattern, then you're viewing the back of the arrow, for example, from this angle here. So to recap, if we see this pattern, then we have the field coming towards us, and if we see this, then we have the field going away. What that means for our example here is that on this side, our field is coming out of the page, whereas on this side, it is going into the page. And so if we grab our right hand and curl our fingers so that they're coming out of the page in this direction and curling into the page on this side, what you'll find is that your thumb is going to be pointing upwards, which indicates the direction of our current. For our second example, we once again take our right hand and point it so that our fingers are coming out of the page on this side and diving into the page on this side. Curling your fingers in this way, you'll find that your thumb is pointing towards the right, which indicates that our current is towards the right. Question 3. The diagrams below show wires carrying a current in a given direction. Label the diagrams to show the distribution of the magnetic field encircling them. In our first example, we have a wire carrying current towards the left. If we take our right hand and point our thumb towards the left, you'll find that your fingers curl into the page atop the wire, and they come out of the page below the wire. And so, of course, we draw our X's up the top and our dots down the bottom. For our next example, we have our current going downwards. Getting our right hand and pointing our thumb downwards, your fingers will curl into the page on this side, so we draw our X's, and they'll curl out of the page on this side, so we draw our dots. In our next example, we just have a dot, which indicates that our current is coming out of the page. If we take our thumb and point it out of the page, your fingers will curl counterclockwise. Similarly, in this example, we have the current going into the page. If you take your right hand and point your thumb into the page, your fingers are going to curl clockwise. Parallel wires. Question 1. Draw arrows on the diagrams below to indicate the force on each wire. In our first example, we have two wires carrying current in the same direction. When wires carry current in the same direction, there is an attractive force between them, and so each wire experiences a force towards the other. In our next example, we have a wire carrying current towards the left and a wire carrying current towards the right. Because these are in opposite directions, there is a repulsive force between the wires. And so we draw our forces away from each wire. In our next example, we have current, which splits into two pathways and then recombines here. That means that we have current traveling in the same direction on each of these branches, which means there's going to be an attractive force between them. In our last example, we have a wire carrying current in a loop. Because we have current traveling towards the right in the bottom, towards the left up the top, these are in opposite directions, and so these sections of wire are going to repel. Question 2. The diagrams below show magnetic fields around two sets of parallel wires. Explain any difference in the total field strength between the wires. The magnetic field strength is indicated by the spacing of the magnetic field lines. The lines between the wires carrying current in the opposite direction, which are these ones here, are spaced more closely. This indicates that the magnetic field is stronger between the wires carrying current in the opposite direction than between the wires carrying current in the same direction. And so if we're looking between the wires are closer in this case here, where the current is traveling in opposite directions, and so the magnetic field strength is going to be stronger. Magnetic force on a current. Question 1. State the direction of the force on the current carrying wires in the diagrams below as either up, down, left, right, into the page, out of the page, or no force. For our first example, we have our magnetic field going into the page, and our current traveling towards the left. Taking our right hand, pointing our thumb in the direction of the current, which is towards the left, and pointing our fingers into the page, our palm faces downwards, which indicates the direction of the force. For our next example, we have our magnetic field lines traveling upwards, and our current is coming out of the page. Taking our right thumb and pointing it out of the page, and our fingers upwards in the direction of the magnetic field, our palm faces towards the left, which indicates the direction of the force. For our third example, we have our magnetic field coming out of the page, and our current traveling upwards. If we take our right hand and point our fingers out of the page in the direction of the magnetic field, and point our thumb upwards, then we have our palm facing towards the right, which is the direction of our force. For our next example, our magnetic field is traveling downwards, and our current is traveling towards the left. Getting our right hand, pointing our fingers downwards, and our thumb towards the left, your palm will now be facing out of the page, which is the direction of our force. In our next example, our magnetic field lines point towards the right, and our current points upwards. Getting your right hand, pointing your fingers towards the right in the direction of the magnetic field, and your thumb upwards in the direction of the current, your palm will now face into the page, which is the direction of our force. Lastly, we have our magnetic field coming out of the page, and our current going into the page. Because these are parallel to each other, they do not generate a force, so we have no force. Question 2. Calculate the magnetic force produced in the following situations. A 2.3 meter wire carries 5.1 amps of current perpendicular to a 0.3 Tesla magnetic field. Our force is given by BIL, where our B is our magnetic field, our I is our current, and our L is our length, which gives us 3.519 or 3.5 newtons to two significant figures. A 1.1 amp current flows in a 1.5 meter wire at a right angle to a 1.2 Tesla magnetic field. Once again, using our F equals BIL, we have our field, we have our current, and we have our length, which gives us 1.98 or 2.0 newtons to two significant figures. A 1.8 meter wire carries 6.2 amps at an angle of 45 degrees to a 0.40 Tesla magnetic field. For this, we take our force equals BIL equation and multiply it by sine of the angle. We know our B, we know our I, our current, we know our length, and we know our angle, which gives me 3.157 or 3.2 newtons to two significant figures. A 9.2 meter wire carrying 2.8 amps is positioned 25 degrees to a 0.70 Tesla magnetic field. Once again, using F equals BIL sine theta, knowing all of these values, gives us 0.7621 or 0.76 newtons to two significant figures. Question 3. A 250 meter section of horizontal power transmission line carries 680 amps of current from east to west. Earth's magnetic field in this region points horizontally south and has a strength of 5 × 10 to the minus 5 Tesla. The wire used has a mass of 1600 kilograms per kilometer. Calculate the gravitational force acting on the section of wire. Gravitational force is mass times gravity, where we know the acceleration due to gravity. And to find our mass, we know that it's 1600 kilograms per kilometer, where we have 0.25 of a kilometer, our 250 meter section, which gives me 400 kilograms. Putting that in gives me 3,920 or 3,900 newtons to two significant figures. In the space below, draw and label the directions of the current, the magnetic field, and the resulting magnetic force on the wire. So we know that our power transmission line carries our current from east to west, so we draw our current line from east to west, and we know that our Earth's magnetic field points horizontally south. and so we draw our magnetic field lines pointing south. Now to find the direction of our force, we get our right hand, we point our thumb towards the left, and we point our fingers down. Doing so, your palm is going to face out of the page, which is the direction of our force. Calculate the magnetic force acting on the wire. We know that this force is equal to BIL, we know our magnetic field, we know our current, and we know our length, which gives us 8.5 newtons. State the direction of the magnetic force. As determined here, we have it coming out of the page. Explain what effect this magnetic force would have on the wire. The magnetic force on the wire points upwards from the ground, opposite to the downwards gravitational force. Because the magnetic force is smaller than the gravitational force, since we found our gravitational force to be 3,900 and our magnetic force to be 8.5, the net force is still downward. However, it is reduced in size from 3,920 to 3,912. Question 4. A magnetic levitation train, or maglev, uses powerful electromagnets to lift the train above the track. During operation, a 0.2 meter section of wire carries 250 amps of current at a right angle to a 0.08 Tesla magnetic field. Calculate the magnetic force acting on the wire. Magnetic force is BIL, we know our B, we know our I, and we know our L, which gives us 4 newtons. The wire is struck by a stone and is now aligned at an angle of 15 degrees to the magnetic field. Calculate the change in the magnetic force. Because we're no longer at a right angle, we need to use our sine theta equation, where we put in our numbers as before, but now sine of our angle as well, which gives us 1.035 or 1.0 newtons to 2 significant figures. And so our magnetic force has decreased from 4 to 1. Question 5. A physicist is investigating how the angle between a 1.2 meter current carrying wire and 0.8 Tesla magnetic field affects the resulting magnetic force. The wire carries a current of 3 amps and is initially perpendicular to the magnetic field. It is then rotated until the force is 1.2 newtons. Calculate the initial magnetic force on the wire. Knowing that force is BIL, our wire is initially perpendicular, so we don't need to worry about sine of the angle. We just need to put in our field, current, and length, which gives us 2.88 or 2.3 newtons to 2 significant figures. Calculate the angle the wire has been rotated through to produce the reduced force. We know that F is equal to BIL sine theta, where we know our BIL, that is the same as it was before, and we know our force that is now present, but we need to find the angle that has reduced it to this value. To solve this equation for our angle, we can first divide both sides by BIL and swap them around, and then take the inverse sine of both sides. Putting in our numbers gives me 24.62 or 25 degrees to 2 significant figures. Explain why the magnetic force decreases as the wire is rotated. The magnetic force is greatest when the direction of current is perpendicular to the magnetic field. When the wire is rotated, the direction of the current is no longer perpendicular to the magnetic field, and the magnetic force is therefore reduced. Magnetic force on a charge. Question 1. State the direction of the force on the charge in the diagrams below. We have a choice of up, down, left, right, into the page, out of the page, and no force. In our first example, we have a positive charge traveling towards the left, and a magnetic field which is pointing up the page. To find the direction of our force, we just use our right hand rule, pointing our thumb towards the left, because that's the direction of our positive charge, and pointing our fingers upwards. We find that our palm, which is the direction of our force, is facing into the page. In our next example, we have a negative charge moving downwards, and a magnetic field pointing out of the page. Because this is a negative charge, we need to point our thumb in the opposite direction to which it's moving. and so we point our thumb upwards and our fingers out of the page. Doing so, you'll find that your palm is facing towards the right, which is the direction of our force. In our next example, we have a positive charge moving towards the right and a magnetic field pointing upwards. Pointing our thumb towards the right and our fingers upwards, we get our palm and therefore the direction of our force facing out of the page. In our next example, we have a positive charge moving downwards and a magnetic field which is pointing into the page. Pointing our thumb downwards and our fingers into the page, our palm is facing towards the right, which is the direction of our force. In our next example, we have a negative charge moving towards the left, and we have a magnetic field which is pointing towards the right. Because these directions are parallel to each other, we have no force. We only have a magnetic force generated when the velocity of the charge and the magnetic field have some perpendicular component relative to each other. In our last example, we have a positive charge moving upwards and a magnetic field pointing out of the page. Pointing our thumb upwards and our fingers out of the page, our palm faces towards the right, which is the direction of our magnetic force. Question 2. For each diagram below, state whether the charge circles clockwise or anti-clockwise. In our first example, a positive charge moves towards the right, and our magnetic field points out of the page. To find the direction of our force, we use the right-hand rule, pointing our thumb towards the right and our fingers out of the page. Our palm faces downwards, which is the direction of this force. And so if our charge is moving in this direction here, but it's experiencing a downward force, then its path is going to curve like this, and so it's going to move clockwise. In our next example, a negative charge moves left through a magnetic field which is pointing into the page. Using our right-hand slap rule, because this is a negative charge, we point our thumb in the opposite direction to its movement, which is towards the right, and our fingers point into the page, which gives us a force pointing upwards. As our charge is moving this way, but our force is moving that way, our trajectory is going to be like this, and so we once again have a clockwise path. In our last example, we have a negative charge moving towards the right through a magnetic field which is pointing out of the page. To find our force, we once again use our right-hand slap rule, pointing our thumb in the opposite direction to the charge movement because it's a negative charge, so our thumb points towards the left. Our fingers point out of the page, which leaves our palm facing upwards, which is the direction of our force. Because our charge is moving this way, and our force is pushing it that way, the trajectory is going to be in this direction, which is anti-clockwise. Question 3. Explain why a charged particle in a magnetic field undergoes circular motion. A charged particle moving in a magnetic field will experience a magnetic force at a right angle to its velocity. We know this because of the right-hand slap rule, which involves pointing our thumb in the direction of the charge velocity, our fingers in the direction of the magnetic field, and our palm therefore pointing in the direction of the force. Whenever we have a force that is perpendicular to velocity, we get circular motion. The magnetic force therefore behaves as a centripetal force, and the particle undergoes circular motion. Question 4. Explain how the following changes would affect the circular path traveled by a charged particle in a magnetic field. Increasing the charge of the object. Increasing the charge on an object will increase the size of the magnetic force, since we know that force is equal to BQV. So if we up the charge, we up the force, which increases the centripetal force. If the centripetal force increases while the charge velocity remains the same, the radius of circular motion will decrease. So if we imagine our F is equal to mv squared over r, if we have an increased force, where our mass and our velocity remain the same, then our radius must decrease, decreasing the strength of the magnetic field. Decreasing the strength of the magnetic field will reduce the size of the magnetic force, since if we have our magnetic field reduce, we have our force reduce as well, which decreases the size of the centripetal force. If the centripetal force decreases while the charge velocity remains the same, the radius of the circular motion will increase. And so similar to before, however, we are decreasing our force, which must result in an increase in the radius if our mass and our velocity remain the same. Increasing the velocity of the charged object. Increasing the velocity of the object while keeping the magnetic field charge and field the same will increase the radius of the circular motion. So knowing that our centripetal force is mv squared over r, and knowing that this is provided by our Lorentz force, our BQV, if our mass, magnetic field and charge stay the same, however we increase the velocity, then our radius must increase as well. Decreasing the mass of the charged object. Decreasing the mass of the object while keeping the centripetal force and velocity the same will decrease the radius of the circular motion. Going back to our equation up here, if we decrease our mass but keep our force and our velocity the same, we must decrease our radius. Question 5. Describe the conditions under which an object in a magnetic field would not experience a force. An object in a magnetic field will not experience a magnetic force if it does not have an electric charge. So if our Q is 0, then our force is going to be 0, or it does not have a component of velocity perpendicular to the magnetic field. Remembering that this equation here is for the case where our magnetic field and our velocity are perpendicular. For the case where they're not, we must multiply this by sine of the angle, where the angle is the angle between our B and our V, and if this is 0, then sine of the angle is 0, and our force is 0. Question 6. Calculate the magnetic force produced in the following situations. An ion with a charge of 5.2 times 10 to the minus 17 coulombs moves with a velocity of 2 times 10 to the 6 meters per second through a 0.12 Tesla magnetic field. Knowing that F is BQV, knowing our B, Q, and V gives us 1.248 times 10 to the minus 11, or 1.2 times 10 to the minus 11 newtons to two significant figures. An electron travels at 6 times 10 to the 6 meters per second through a 0.025 Tesla magnetic field. Once again, F is BQV. We know our B, we're given it in the question. We know the charge of an electron, and we're given our velocity, which gives me negative 2.4 times 10 to the negative 14 newtons. Question 7. Calculate the velocity of the objects in the following situations. A raindrop with a charge of negative 6 times 10 to the minus 7 coulombs experiences a 3.7 times 10 to the minus 8 Newton magnetic force as it falls through a 0.02 Tesla magnetic field. Knowing that F is BQV, we can solve for V by dividing both sides by BQ. Putting our numbers in gives me negative 3.083 or 3.1 meters per second to two significant figures. A pollen grain with a charge of 8 times 10 to the minus 7 coulombs experiences a 4 times 10 to the minus 8 Newton magnetic force as it drifts through a 0.025 Tesla magnetic field. Once again, F is BQV, solving that for V, putting in our numbers, gives me 2.0 meters per second. Question 8. A small asteroid carrying a charge of 2 times 10 to the 5 coulombs travels through the sun's magnetic field at a speed of 4 times 10 to the 3 meters per second. The magnetic field in this region has a strength of 5 times 10 to the minus 9 Tesla. Calculate the magnitude of the magnetic force acting on the asteroid. F is BQV. We're given all of these things in the question, which gives us 4 newtons. Explain how the magnetic force would change if the speed of the asteroid was doubled. The magnetic force is equal to BQV. If the magnetic field strength and charge stay the same, doubling the speed of the asteroid will double the size of the magnetic force. Voltage induced in a wire. Question 1. The diagrams below show metal rods moving through uniform magnetic fields. Label the positive and negative ends of each rod. We have a magnetic field going out of the page, and a rod traveling towards the left. If we take our right hand and point our fingers out of the page and our fingers towards the left, we'll find our palm facing upwards, which is the direction that a positive charge would experience a force, and so the top end is positive, which must leave the bottom end negative. In our next example, our field is going into the page, and our rod is moving upwards. Once again, taking our right hand, putting our fingers into the page, and pointing our thumb upwards, our palm faces towards the left, which is the direction that positive charges are forced, and so the other end must be negative. For our next example, our magnetic field is going out of the page, our rod is going towards the right, pointing our fingers out of the page, and our thumb towards the right, our palm faces downwards, which means the bottom end must be positive, and the top end must be negative. For our last example, the field is going into the page, and our rod is moving towards the left. Taking our right hand, pointing our fingers into the page and our thumb towards the left, our palm faces downwards, which is the direction that our positive charges are forced, which leaves the top of our rod negative. Question 2. A conductive wire rotates through a uniform magnetic field as shown below. So we have our position A and our position B. So our conductive wire is rotating like this. Explain what happens to the size of the induced voltage at each position. The magnetic field lines point horizontally from right to left. Our magnetic field lines always point towards south, and so they point towards the left. When the wire is at position A, the velocity points vertically. So if we consider any particle in our rod, then at this position, their velocities are going to be vertical. Because it has a component perpendicular to the magnetic field, it generates a voltage. When the wire is at position B, the velocity points horizontally. So if we consider any particle in our wire again, at this position, their velocities are going to be horizontal. Because it does not have a component perpendicular to the magnetic field, as the magnetic field is also horizontal, it does not generate a voltage. Question 3. Calculate the voltage induced in the following situations. A 0.54 meter metal rod moves through a 0.25 Tesla magnetic field at 3 meters per second. Knowing that the voltage is BVL, knowing our B, knowing our V, our velocity, and our L, our length, gives us 0.405 or 0.41 volts to two significant figures. A 1.5 metal bar slides along a tabletop at 2.5 meters per second through a 0.058 Tesla magnetic field. Once again, our voltage is BVL, we know our B, we know our velocity, and we know our length, which gives us 0.2175 or 0.22 volts to two significant figures. Our next example is a diagram showing a magnetic field going into the page, which has a height of 10 centimeters. The strength of our field is 0.26 Tesla. We have a 12 centimeter rod, which is traveling at 1.5 meters per second towards the right. The trick here is to make sure you choose the correct length. The correct length is our 10 centimeters or 0.1 meters, because this is the length of the rod in the field. The ends of the rod that are not in the field do not contribute towards the effect, and so we can't use the 12 centimeters. Knowing V is BVL, knowing our B, our velocity, and our correct L gives us 0.039 volts. In our next example, we have a magnetic field of 0.15 Tesla pointing into the page. The field has a height of 40 millimeters, and we have a 30 millimeter rod traveling at 0.44 meters per second towards the right. The correct length is our 30 millimeters or 0.03 meters, because this is the length of the rod in the field. We don't use our 40 because we must use the length of the rod in the field, and the length of the rod is not as large as the field. It's smaller. And so once again, V is BVL. We know all three of these things, which gives us 1.98 times 10 to the minus 3, or 2 times 10 to the minus 3 volts to two significant figures. Question 4.
A straight wire moves through a 0.4 Tesla magnetic field at 3 meters per second, creating an induced voltage of 12 volts. Calculate the length of the wire. V is equal to BVL. To find the length, we divide both sides by BV, put in our voltage, our field, and our velocity, gives us 1 meter. Question 5. A 1 meter rod moves through a 0.2 Tesla magnetic field, producing a voltage of 0.5 volts. Calculate the velocity of the rod. V is BVL. To solve for our lowercase v, our velocity, we divide both sides by BL. Putting in our voltage, our field, and our length gives us 2.5 meters per second. Question 6. A solar probe is launched to study the Sun's outer atmosphere. During part of its mission, a 2-meter section of its conducting antenna moves at a right angle to the Sun's magnetic field with a velocity of 1.5 times 10 to the 5 meters per second. An induced voltage of 24 volts is measured across the antenna. Calculate the magnetic field strength at this location. V is equal to BVL. To find our B, we divide both sides by VL. Putting in our voltage, our velocity, and our length gives us 8.0 times 10 to the minus 5 Tesla. Explain how the induced voltage would change if the antenna was not moving perpendicular to the magnetic field. The maximum induced voltage is experienced when the antenna moves perpendicular to the magnetic field. The further the antenna velocity and magnetic field are from being perpendicular, the less the induced voltage. If the antenna traveled parallel to the field, there would be no induced voltage. A section of the probe's antenna breaks off, causing the induced voltage to drop to 10 volts. Calculate the length of the missing section of antenna. First of all, we're going to use our V equals BVL equation, solve for our length, to find the new length of our antenna. Putting our new voltage, our field, and our velocity in gives us 0.8333 meters. And now we aren't asked for this length here, we are specifically asked for the length of the missing section. To find our missing L, we start with our initial length of 2 meters and subtract our remaining length, which gives us 1.167 or 1.2 meters to two significant figures. Question 7. A research aircraft flies over Antarctica at 830 kilometers per hour, studying variations in Earth's magnetic field. A 53-meter conducting rod is mounted across the aircraft's wingspan. The aircraft flies perpendicular to Earth's magnetic field, then changes direction by 30 degrees, causing the induced voltage to decrease by 1.6 volts. Calculate the strength of Earth's magnetic field. First of all, our velocity of 830 kilometers per hour is 230.6 meters per second. To convert this, we can just divide by 3.6. In our situation described, we have our magnetic field lines from the Earth, and our aircraft has gone from flying perpendicular to flying 30 degrees from perpendicular. To find our change in voltage, that is just our final minus our initial, where our initial is perpendicular, and so we can just use BVL. However, our final is at an angle, so we use BVL sine theta, where theta is the angle between the direction of the velocity and the magnetic field, which is not our 30 degrees, it is 90 minus 30, which is 60 degrees. Solving this equation for our magnetic field strength, we can first factorize it out, and then divide both sides by our brackets and swap them around. Putting in all of our numbers gives me negative 0.00097772 or negative 0.00098 Teslas to two significant figures. Loops moving in magnetic fields. Question 1. The diagrams below show a loop of wire entering a uniform magnetic field at a constant speed. Explain the size and direction of the current in the loop at each stage. In our first stage, we have our loop of wire completely outside our magnetic field. And so the loop is outside the magnetic field, therefore no voltage is induced and no current flows. In our next stage, our loop of wire is just entering our magnetic field. To find the direction of the force on our positive charges, we use our right hand rule, where our fingers point in the direction of the field, which is into the page, and our thumb points towards the right, which is the velocity of our charges. Doing so, our palm faces upwards, indicating that positive charges in this loop are going to be forced upwards when they're in this magnetic field pointing into the page. And so positive charges are forced upwards in the right section as it's inside the magnetic field. This causes a counterclockwise current. And so this section is in the magnetic field, and so it contributes to the effect. We get positive charges being forced upwards, which creates a counterclockwise current. We get no effect from this section because it's not in the magnetic field, and our top and bottom sections don't contribute to the effect because the positive charges are forced upwards, and in these two sections there is no conductor for them to move upwards into. All that really happens is that the charges get separated over the width of this wire, which really doesn't do anything for our overall current. In our next stage, our entire loop is inside our magnetic field, and so both left and right sections are within the field and experience equal and opposite voltages. These cancel and cause no current to flow. So our positive charges are forced upwards in both sides of the loop, and these effects are in opposition to each other and therefore cancel out, leaving no current flowing. In our last section, our loop of wire is exiting the magnetic field, and it's only our left section that is inside the magnetic field. Positive charges are forced upwards in the left section as it's inside the magnetic field. This causes a clockwise current. So our positive charges being forced upwards creates our clockwise current. Question 2. Plot the current in the loop as a function of time on the graph below. With current on our y-axis, in our first section we have no current flowing, and then we have a counterclockwise current, which in this case I'm going to make positive. This is an arbitrary decision. I could just as well have made it negative, as long as if I have a clockwise current, I make that the opposite sign. In our next section, we once again have no current flowing, and in our last section we have a clockwise current, and so our current is negative, since we made our counterclockwise current positive. And so, just to make myself clear, if we instead decided to make clockwise currents positive, then our graph would look like this, and that is a perfectly acceptable answer. Question 3. Explain why current does not flow through the lamp in the following situations. In this situation here, we have a magnetic field going into the page, and we have a wire loop with a bulb which is moving towards the right. And now, although positive charges experience an upwards force in both the left and right sections, their induced voltages oppose and cancel. The top of the loop becomes positively charged and the bottom of the loop becomes negatively charged. However, no current flows. So our positive charges are forced to the top and our negative charges are forced to the bottom, leaving us just with a separation of charge and no current flowing. In our next situation, we once again have a magnetic field into the page and a length of wire with a bulb moving towards the right. Positive charges experience a force upwards through the wire, however the wire does not form a circuit, so current is unable to flow. Instead, the top of the wire remains positively charged and the bottom negatively charged. So we get a positively charged top and a negatively charged bottom, but because this isn't a circuit, the charges are unable to loop back around and make current flow. Once the charges have separated, we get no current flowing, so our lamp will not glow. Question 4. The coils of wire below rotate so their outer edges cross the 1.2 Tesla magnetic field at 2.5 meters per second. Calculate the maximum voltage generated by the rotating coils. In our first situation, we have our south and north poles. We have a loop of wire that is 2 centimeters by 1.5, and we see that it is rotating in the clockwise direction. The sections of wire contributing to our voltage are these two sections here. The force on our charges in these top and bottom sections are in either this direction or that direction, in which there's no conductor for charges to flow, and so they don't contribute to the voltage generated by the coil. And so our length is 2 times our 2 centimeters, which is 0.04 meters. Knowing that our voltage is BVL, knowing our B, our velocity, and our L that we just found, we get 0.12 volts. In our next example, we have our south and north pole, our loop of wire, which is 12 millimeters by 20 millimeters. And once again, that's rotating clockwise. The direction that it's rotating in is irrelevant in this case. The magnitude of our voltage will be the same. As with our last question, it's only these 12 millimeter sections that contribute towards our coil voltage, and so our length is 2 times our 12 millimeters, which is 0.024 meters. Once again, using V equals BVL, knowing our field, our velocity, and our length gives us 0.072 volts. Question 5. An 18 centimeter by 1.4 centimeter coil of wire rotates through a 0.4 Tesla magnetic field as shown below. The long edges rotate through the magnetic field at 4 meters per second. The coil consists of multiple loops and generates a peak voltage of 1.2 volts. Explain how the movement of the coil causes current to flow. First of all, the magnetic field lines point north to south, which is towards the left. So in this direction here. As the coil rotates, the left side moves out of the page and the right side moves into the page. So because our coil is rotating clockwise, this section is moving up and this section is moving down into the page. Positive charges are forced downwards in the left side and upward in the right side. To confirm this direction, we take our right hand and point our fingers in the direction of our south pole, pointing our thumb upwards. Our palm is facing downwards, indicating that positive charges in the left section are going to be forced downwards. If we instead point our thumb into the page, which is the case with the right section, we instead find our palm facing upwards, and so our positive charges are forced upwards in the right section. This causes an anti-clockwise current to flow. Since these influences aren't in opposition to each other, they combine to form an anti-clockwise current. The top and bottom sections do not provide a path for charges to move up or down into, so they do not contribute to the flow of current. Calculate the induced voltage produced by a single loop. As we've established, the only sections contributing to our effect are these two 1.8 centimeter sections. So our length is 2 times 1.8, which is 0.036 meters. Our voltage is BVL. We know our B, we know our V, and we know our L, which gives me 0.0576 or 0.058 volts to two significant figures. Calculate the total number of loops in the coil. Our number of loops is going to be our total voltage divided by the voltage of a single loop, since each of these single loops is contributing towards the total voltage. Our total voltage is 1.2, and we just found our voltage of the single loop, which gives us 20.83 or 21 to two significant figures.